And the year was 1916, where the still best and most successful theory was Niels Bohr quantum theory, which had been recently generalized by Arnold Sommerfeld to the case of the hydrogen atom. Nevertheless, this Niels Bohr quantum theory still faced a lot of problems. It couldn't explain a lot of results. One of these was the anomalous Zeeman effect, which hadn't been explained yet. Another important thing happening at the time was this famous debate between classical and quantum mechanics, where many physicists really hadn't decided in which theory they relied on best. So in 1921, what Arthur Stern and Walter Gerlach proposed to do was to measure a property that was only predicted in quantum theory. This was space quantization, which really is just quantization of angular momentum. And so if these results proved positive, it would confirm quantum theory once again, and it would make classical mechanics impossible to sustain. Nevertheless, many important things were happening at this time. For example, World War I was of great importance for these scientists because they struggled a lot to get the funding they needed. So, well, in the end, this experiment was extremely important because it confirmed once again quantum theory. And we can see this by contradiction originating from classical mechanics. In classical mechanics, angular momentum is defined as L equals the moment of inertia times the angular velocity. Here we can see we have an expression for the moment of inertia of a solid sphere. In the case of an electron, for example, we're talking about something that resembles a point particle. So in the limit as r tends to 0, the angular momentum would be 0 unless the angular velocity was greater than the speed of light in the case of the electron, the angular velocity of its surface, which is clearly a contradiction. So this couldn't happen, and it didn't. In the end, this experiment hinted physicists a little bit in the direction of spin, which is sort of an intrinsic angular momentum carried by elementary particles. And it also offered a hint to solve this problem about the moment of inertia. And it guided physicists towards what was the next evolution of quantum theory, which was relativistic quantum mechanics, which in the end would turn out to be quantum field theory. So the importance of this experiment cannot be underemphasized.
In the Stern-Gerlach experiment, there were used atoms of silver because silver atoms have 47 electrons, of which 46 fill completely the n equal 1, 2, 3, and 4 levels of energy. The last electron is an n equal 5 electron with a 0 orbital angular momentum, also called a 5s state. This property makes that when shooting silver atoms, essentially you're throwing electrons for the purpose of this experiment at least. So that the only possible angular momentum is the intrinsic angular momentum of the last electron. In this case, the nucleus has a much smaller dipole moment due to its mass and can be ignored. To start the experiment, the silver is vaporized in an oven at high temperatures, approximately at 1000 degrees Celsius. Then, the gas is passed through a collimating slit consisting of 2 thin parallel slots in order to get a narrow beam of silver atoms. After that, the beam of silver atoms is passed through a non-uniform magnetic field created in the gap between the pole faces of a large magnet with a specific shape, which is shown in the slide. And finally, the beam is then detected by being deposited on a glass collector plate. Even so, the magnetic field is not uniform due to the shape of the magnetic field and the gradient point mostly in the positive z direction. As a result, the atoms experience a force in the z direction proportional to the z component of the magnetic moment. Having that in mind, and from the classical perspective, undeflected atoms will be expected to hit the detector screen exactly at the center. Atoms with positive magnetic moment in the z direction should be deflected upwards, and atoms with a negative magnetic moment in the z direction should be deflected downwards.
So Otto Stern and Wilhelm Gerlach were two atomic physicists who were interested to know what happened with the orbital magnetic momentum of silver atoms according to Bohr's theory. And the important part of silver, and the key element, is that according to chemistry, its electron configuration is about 47 electrons, and at the last orbit, it has a free electron. So what these guys managed to create was basically a spin gun. So that's the main reason of why they got that bizarre pattern. And as the history of quantum mechanics goes back, it is an intertwine between statistical mechanics and quantum mechanics, information that you can extrapolate. Because these guys used the key idea of thermal equilibrium to, as we discussed earlier, analyze what happens with the magnetic orbital momentum of silver. And as we know, they got to spin. And one key element of this spin properties is its orthogonality, because one of the most important misconceptions of itself is that we have both two spins, that one pointing up and one pointing down. But as we know, it is not like that, and it is a superposition of different spins, which yields the behavior of spin-like particles.
Okay, well, now speaking about the results of the experiment, it is actually very interesting because the Stern-Gerlach experiment was originally conceived to demonstrate the space quantization associated with orbiting electrons in atoms. Now, before going to the specific results, we need to remember some of the key points of the experiment that consisted on a beam of silver atoms that passed through a non-uniform magnetic field created in the gap between the pole faces of a large magnet. This beam was then detected by being deposited on a glass collector plate. Now, the importance of this magnetic non-uniform field was that it exerts a force for any magnetic moment so that each atom is deflected in the gap by an amount governed by the orientation of its moment with respect to the direction of inhomogeneity, that in this case was the z-axis. Now, the results were actually very interesting because if the moment directions are restricted by space quantization, as in the figure that we have in the back of this presentation, so too are the deflections. Thus, the atomic beam should split into a number of discrete components, one of each distinct moment orientation present in the beam. However, when the results were clear for the scientists, the silver atomic beam was clearly split, but into only two components, not the odd number 2L plus 1 that was expected for the space quantization of orbital momentum. This result was so impressive that it was actually repeated. The experiment was repeated by T.E. Phillips and J.B. Taylor in 1927, but with the hydrogen atom replacing silver, thereby eliminating any uncertainties arising from the use of more complex silver atoms. The results, however, were unchanged. And well, in the end, this gave us some information about a very important fact about the particles, that is the spin up and the spin down. That spin up is attributed to the +1 halves and the spin down is attributed to the -1 half. This is a very important result because we have seen that now there are more facts that are actually giving some contribution to the atom. And well, here we have some pictures about the experiment and the results, and it is actually very interesting. But well, in the end, this is science.
Now with applications part. The quantization of the spin property is used in various fields of study, like for example, in the medicine field. In the medicine field, it's used in the magnetic resonance imaging, which is found in hospitals and is used to see images of the insides of the body without having to expose it to dangerous types of radiations. Now, first of all, we have to define this type of movement, which is the precession. The precession is when you change the rotating axis of a particle, like for example, in the image depicted in the left side of the slide. Now, the following principle is this. The hydrogen atom that composes the body in form of water are exposed to an external magnetic field that is generated by the magnet in the MRI equipment. Now, these hydrogen atoms behave as magnets, so they align their axis in which they precess with the direction of the magnetic field, which could be parallel or antiparallelly to the magnetic field according with the spin. Now, continuing with the magnet, a series of sounds starts, which are the gradient coils, that consist of copper coils which are experimenting an electric current and generating magnetic fields. These coils are experimenting these currents for really short periods of time to generate higher frequencies. These higher frequencies are generated with the purpose so that they resonate with the resonating of the hydrogen atoms. By this resonance, we obtain information about their position, and the information is obtained by an antenna and then processed by a computer, and through densities of the atoms, we create the contrast of images. This is very useful because we don't have to submit the body to dangerous types of radiation such as gamma rays or X-rays. This is because of the energy that the atoms are experiencing. So it's a very useful application that we can see in the quantization of the spin property that was discovered in the Stern-Gerlach experiment.